So this lesson is going to talk about inverses. And so we're going to show you a couple of different things, give you a summary, and then show you some examples. So first off, I want you guys to see what we're looking at when we're talking about inverses. We want to know, how do we know that functions are inverses? How do we find an inverse function? And so there's three really standout ways that you can kind of see if things are inverses. And that is numerically, graphically, or algebraically. So first, we are going to look at actually the graphically version. And so I'm going to show you guys a picture here. So this gives you a good idea of what inverse functions look like. Now, you see in each graph, here there's an f of x, and then there's an f with a little -1. So that's the first thing I'm going to note right there, is that the way that we say this is f inverse. That means if you know what the f function is, like we've been naming them when we were doing our operations and our composition, this -1 isn't really an exponent. It's indicating that they are referring to the f function, but the inverse of that f function, not the original f function. And what you can see on these graphs is that when we have inverse functions, they're reflected over the line y equals x. Okay? So it's like taking and reflecting, but not over the x-axis or the y-axis, instead over the line y equals x. So that's what we're going to write down for our graphical summary, that inverse functions are reflections over the line y equals x. The next thing we want to understand is, what does that mean numerically? Like, how did they get that reflection over the line y equals x? What happened to the numbers, the plugging in and plugging out, the numbers that you get in the function? So I'm going to show you that relationship here. So in the circles here, you see f and then f inverse. So f says that a, if you plug in a, you get out 3. If you plug in b, you get out 1. If you plug in c, you get out 2. Look at it, f inverse, it says if you plug in 1, you get out b. If you plug in 2, you get out c. If you plug in 3, you get out a. And then over here, it's in a chart format. If these are points in the f function, so look at the chart underneath f, has -2, 4, -1, 6, 0, -7, 1, 1, 2, 8. If you look at f inverse, it has -2, 4, -1, 6, 0, -7, 1, 1, and 2, 8. So those look exactly the same. And so this f inverse function should actually look a little bit different. So let's talk about how the inverse function would be adjusted. I'm going to put that here in our number chart. How should this have been adjusted? So when we look at numerically, x and y coordinates are exchanged. So when I look back at that chart, use that example again, that's not totally complete. We want to complete these charts like we see over here with the circles. So I look at the chart, it has -2, 4, -1, 6, 0, -7. We'll just use those three. So it has -2, 4, -1, 6, 0, -7. These were points in the function f. The first column was the inputs and the second column was what you get out, the outputs. If you were to build the inverse function, because of the reflection over the line y equals x, the x's from the original function equal the y's, and the y's from the original function will equal the x's. So you're going to see this switch, that this would have the point 4, -2, 6, -1, and -7, 0. That's what you're going to see numerically. Now, since the main idea of inverse functions is that they undo each other, algebraically, how we could tell, so there's two things that happen algebraically. There's two different types of things you might be able to do. If you're trying to prove that two things are inverses versus if you're trying to find an inverse. Okay, so the first thing I'm going to talk about is, how do we prove two things are inverses? So algebraically, if someone says, here's two functions, they're inverses. I say, oh, okay, I understand what this means. If I drew them, they're reflected over the line y equals x. If I look at their coordinates, the x's and the y's should be switched. So these functions are supposed to undo each other. So for example, look at our charts over here and think about our composition. Let's say we did f of f inverse of 4. Okay. First, you would calculate f inverse of 4. Here's an input of 4 in f inverse, and the output is -2. That means this would get replaced with -2. And now you would be going to find f of -2. Here's a -2 input in the f function, and the output is 4. So this means f of f inverse is 4. Excuse me, f inverse of 4 is 4. Okay. Let's say we did it a different direction. Let's say we found f inverse of f of -1. Start with the f function and look at an input of -1 gives us an output of 6. So we can replace this with 6. And now go to the f inverse function and calculate f inverse of 6. When 6 is the input of the inverse function, -1 is the output. So f inverse of f of -1 turned out to be -1. So you kind of see the pattern. Well, of course it's going to be if -1 got turned into 6, but then when you plug 6 into the next one, it gets turned back into -1 because they are undoing each other. So if you wanted to check and see if functions are inverses algebraically, you would check exactly the compositions that we just said. Do they undo each other? If I find a point in one and then plug that answer into the next, does it take me back to the original value? So that means, does f of f inverse of x get me back to x? And, meaning both of these things have to be true, not just one way, f inverse of f of x would also have to get us back to x. So we would have to check both of those compositions and see that we got x, and then we would know they are for certain inverses, okay? Now, the other thing I was talking about is if you're finding inverses algebraically. So these are two different questions. In the first question, when I'm proving things are inverses, someone's saying, here's two functions, they are inverses, and I'm trying to prove it to myself with composition. The second idea is if someone says, hey, here's a function, what is its inverse? Okay. And to find the inverse, we are going to switch x and y and solve for y to write it like a function that we normally do. And then I'm going to add a little asterisk here about being careful with domain and range. If the x's and y's are switching, then the domain of the first function should become the range of the second function. That means sometimes there are restrictions that we have to take into account when we're finding inverses. Okay. All right, so we're going to look first at these two examples. Example 16. We'll actually just look at one. So we'll look at part A. And we're determining or proving that the functions are inverses. So are f and g inverses? That's the question. And we have two ways we're going to look at this, algebraically and graphically. The reason we're not doing numerically is because to prove something is true with numbers, you would have to prove it happens for every number. So you would be infinitely stuck here doing this. So we're going to do more general methods with graphs and algebra. So for the algebra, I'm going to have to check that f of f, excuse me, they didn't call it f inverse yet because we don't know if it's true. So f of g of x, does it equal x? That's my question mark. And I would need g of f of x to also equal x. Does that work? So I'm checking these two things. Okay, so first let's work on f of g of x. So this is me plugging the g function in. That would look like this. Now I'm going to plug that into f. So remember how we do this. Some of you guys struggled with this on the test. Here's my f function. I'm plugging in this expression x plus 4 over 3 where x normally is, and I'm simplifying. So when these multiply, the 3's will cancel out, and I will have x plus 4 and then minus 4. The positive 4 and the negative 4 will cancel out, and I'll get x. That is what I wanted. So this checks f of g of x is equal to x. But I can't stop there. It has to work in both directions. So I now need to check g of f of x. So I'm going to replace f of x with its function, 3x minus 4. And then remember, how do I plug 3x minus 4 into the g function? I write the g function with an empty set of parentheses representing where I can plug stuff in. And then I plug in the quantity that's been given here, which is 3x minus 4. Now in this case, the minus 4 and the plus 4 will add up to 0. We'll have 3x over 3. The 3's will cancel, and we'll have x. So this also worked. Because both of these compositions worked, then these are inverses. If either one of them did not work, then we would not have inverses. Okay. So now that I already know that, I kind of know what I expect to see on the graph, but I'm still going to go ahead and graph these. So I'm going to graph f of x in red. So it's the line 3x minus 4. So I'm going to start at my y-intercept of -4 and have a slope that rises 3 and runs 1. And I need to draw a few dots on here, otherwise I'm not very good at drawing the straight line. So there's f of x. I'm going to graph g of x in blue. And I'm going to rewrite it for those of you that this looks a little confusing. I'm going to think of this as 1/3 x plus 4/3. So my y-intercept is 4/3, or excuse me, 1 1/3. And then my slope is up 1 over 3. Or down 1 into the left 3. That can work too. And then I'm going to go ahead and draw that line. And if these are inverses, which I already know they are because I did this 2 ways, right? And the algebra already told me they are. I should see that they're reflections over the line y equals x. So let me label my g function first. And then for the line y equals x, keep in mind what that is. That's a line with a y-intercept at 0 and a slope of 1. So it is just this dashed line that starts at the origin and has a slope of +1. So it looks like this. And you can see that if we folded our graph over that line, all the red and blue portions would lay on top of each other because this is a reflection over the line y equals x. So those are our 2 methods for proof. Again, we can't use the numbers for proof because you would have to prove infinitely many cases. All right, so now we're going to work on finding the inverse ourselves. Okay, so this is that second algebraic idea. In the previous example, we were making sure they were inverses or proving or determining they were inverses, and here we're finding inverses. Okay, and so the word relation, we use the word function often in lieu of this, but we really shouldn't. A relation means points that don't necessarily follow the function rule. A function means a set of points that do follow that rule. So they're just saying, here's a set of points. Can you find the inverse? So remember, the inverse just has the x's and y's switched. So when it is just a set of points, I literally can just rewrite the points like we did in that chart earlier, where the y's become the x's and the x's become the y's. So this is the original relation, and this is its inverse. And then you'll often be asked if they are functions. And because we use that word loosely sometimes, you forget it has a really strict definition. Functions have to be relations where every input only has one output. So this first relation had -1 going to -2, but then -1 showed up again going to a different output. That would fail the vertical line test. It's not a function, and neither is its inverse because it also has that same issue. So these are inverses, but they are not inverse functions. Okay, so you can't just say inverses for short. Inverse means the inputs and outputs have switched. Inverse functions means not only have the inputs and outputs switched, but they're both functions. Okay. All right, so when I look at this next example, I'm going to think of it as y equals 1/2 x plus 2. This is the original relation, okay? Is this a function? This is, okay? Because any line that's not a vertical line that has some sort of slant to it, We'll pass the vertical line test anywhere on the graph. There's only one x for every one y. So this is the original, and it is a function. So now the work to find the inverse. So we know that numerically the x and y values switch. So we're going to do that here, but just hold the place of x and y with our variables. So I'm going to literally switch the variables x and y. And now the inputs are where the outputs used to be, and the outputs are where the inputs used to be. But I'm going to solve it for y because that's how we normally write our functions. So this will say x minus 2 equals 1/2 y. And then I will multiply by 2. And I will have y equals 2x minus 4. This is the inverse. And then is it also a function? Okay. And it is an inverse function because, again, it is a line. It's a little steeper, but it would pass the vertical line test. So this is an inverse function. I can say that word with it. All right, so now we're going to look at the quadratic, and we're going to get a little more specific here. So I want to give you a little reminder. So this is our original, the quadratic. And it is a function. It passes the vertical line test, right? It looks something like this. And then just a small reminder, its domain is all real numbers for this quadratic, and its range would depend on this vertex point, which, given that it's written in vertex form, I can see as 2, -3. So y is greater than or equal to -3. Now, what I'm going to do is I'm going to write an inverse. I don't know if it's going to be a function yet. So this is something I have to figure out. And its domain should be x's are bigger than or equal to -3, and its range should be all real numbers. So that is because of the domain and the range in the original function. Okay, so let's go through the process to solve. So I'm going to rewrite my original function with x and y. I'm going to switch x and y to make my inverse. So right here, I have officially written a new equation that is the inverse, but I'm going to rewrite it in the form we're used to seeing in it, and then decide if it's a function. Now I have to square root here to solve this, and I'm going to have to use plus or minus. And so I'm going to end up with the equation that says -2 plus or minus the square root of x plus 3. Now, you might not be familiar with what that looks like, but if you think a little more closely, you do know. This is a square root function, okay? This is like having y equals square root of x plus 3 and then minus 2 at the end. So you can see your h is -3, your k is -2. So this would look like -3, -2, and it's a square root function and we know its shape. But with the plus or minus, this is actually two functions put together. It also is this other function. So that has the same point, but it gets reflected vertically, and notice it looks kind of like a sideways parabola. And you can see there that the domain is x is greater than or equal to -3. The range would be all real numbers, but you can also see it's not a function. Okay, it would not pass the vertical line test. Okay. All right, I'm going to change this last example to a square root just because they're a little more difficult. So we're going to think of our original function here as a square root. So this is our original. It is a function. I know that it looks something like this because I know the square root functions. And if I think of it slightly different just for a minute to understand exactly where the points are, this has a vertex point at 5/2, 0. That means its domain is x's that are bigger than or equal to 5/2, and its range is y's that are greater than or equal to 0. This is going to be extra important in this problem, and this is why I changed it to a square root. So we know the original is a function. We're going to find the inverse. I wrote the domains and ranges because remember, we want to pay attention to what happens to those as well. So I'm going to switch x and y, which means I have officially written an inverse, but now I'm going to rewrite it in the format we're used to, so I'm going to solve for y. So I need to square both sides and then finish solving for y. So I would add 5 and divide by 2. So I get y equals 1/2 x squared plus 5/2. Now, I want you to think for a minute about what this is. This is a quadratic facing upward. So this is something like this. That does not look like the reflection of this original graph because this graph only has one piece to it. But that's because this function can only have a domain where x is greater than or equal to 0 and a range where y is greater than or equal to 5/2 based on the original function's domain and range. The inverse has to have those switched. So when we write this inverse will be written as the equation you found, but with a restriction that x's can only be greater than or equal to 0. So you're not getting the whole parabola, you're not getting this part of it, you're just getting this part of it. And then they look more like inverses. Okay, so that's an inverse. It is a function. And then we have here what its domain and range would be as well. Okay. All right. We're going to look at sketches and then applications. So sketching, we just want to focus on the reflection aspect. And I'm just going to do part A again. So again, if you know something is an inverse, you know that it's reflected over the line y equals x. This reflection can be hard to draw, so my advice to you is to pick out some points. Like in the original here, I see the point. So in the original, I have the point 0, 2. I also have a point here at -3, 0. And a point here at 3, 0. Okay, let's see if I can use those to help me draw my inverse a little bit. I know I'm supposed to reflect it, but sometimes my spatial ability is not so great. So the inverse I know should reflect over this line, but if I struggle with that, I can also invert the points. So I know I should have the point 2, 0, 0, -3, and 0, 3. So that might help guide me a little bit. Like here's 0, -3. Here's 0, 3. Here's 2, 0. And they'll share this point right here on the axis. So this will go something like this. And then you can kind of see that reflection a little bit better. So if you're struggling with drawing the inverses, I would say to use some points to help you. Okay. Now, we can look at these and determine if they are functions. So look at the original function. I'm going to name them. Let's call it f. It would pass the vertical line test. It's like a quadratic. So f is a function. When I look at the inverse that I drew in blue, it would fail the vertical line test. It's not a function. Our question becomes, can we tell that something, an inverse, is or is not a function before we graph it? Okay, so if we just had this function and you knew your original function looked like this, understanding what an inverse is, could you understand right away if this is a function and if its inverse is a function? So we already know the vertical line test tests to see if the graph is a function. The graph you are actually viewing is a function, like we said. So this one passes, it's a function. There is another test called the horizontal line test. So the lines are running the other way, like a reflection of a vertical line, okay? It tests an original graph, but it doesn't actually tell you anything about this graph. So I'm going to test it this way. You can see it's failing the horizontal line test. It's hitting more than once. That tells me nothing about the original. I test the original to determine if the inverse is a function. Okay, so that's what our horizontal line test will do. So you can draw it and then test it and just use vertical lines, or you could use the horizontal line test on the original. So I could look at this one and I could say passes the vertical line test, this is a function. Fails the horizontal line test, so I know its inverse is not a function. And this must not be 1-to-1, okay? Because it didn't pass both. All right, the last thing we're going to do is just look at how do we interpret inverses, okay? So we're going to put them in a situation. So for example 19, there's a graph here, and it says it's the function f of x. So f of x is the name of our function. And it represents the number of songs that Elton has learned to play on his piano after X months. So this X is months. And then the Y represents the number of songs he has learned after so many months. So when I look at this, this means after 1 month, he's learned 4 songs. After 2 months, he knows 6 songs. After 3 months, he knows 8 songs, etc. Okay? So then the first question is, what is the value of f inverse of 4? So if somebody asks me f of 4, they're giving me the number of months, and I'm supposed to determine the number of songs. Okay, and after 4 months, it is 10 songs. That was not their question. Their question is f inverse of 4. Remember, the inverse has switched the x and the y. So that means the input is no longer months. The input is the number of songs. And the output will be the number of months. Okay? And you would actually be looking for a y value of 4 on the original graph. Because remember, if you made a chart for this original function, okay, and let's see, it had 1, 4, 2, 6, 3, 8, 4, 10, then the inverse would have 4, 1, 2, 6, 6, 2, 8, 3, and 10, 4. So f inverse of 4 means when you input 4 to the inverse, you get out 1. So if we wanted to look at it on the graph, we would be actually looking for a y value of 4 because we're looking for an input for the inverse. The input for the inverse is the output of the original function, and then that lines up with 1. All right, and what does this mean in context? It means he learned 4 songs after 1 month. Notice the meaning is the same both ways. If I say f of 1 equals 4, this means after 1 month, he learned 4 songs. F inverse of 4 equals 1, he learned 4 songs after 1 month. We're just saying it in a different order, viewing it in a different way. All right. So here's another example, number 20. X is the Celsius temperature of an object, and f of x is the Fahrenheit temperature. Okay. And so this shows us if it's negative 23 1/3 degrees Celsius, that is equivalent to negative 10 degrees Fahrenheit. Okay. And this chart is for F. So understand, if you made an F inverse chart, you would have Fahrenheit in the X column and Celsius in the Y column, but the same numbers would still be associated together and represent the same measurements. So this would be what I would be thinking about if I made a new chart for the inverse function. The only difference is it's not changing what amount Celsius is the same as what amount Fahrenheit. Those are constant. It's just that F plugs in Celsius and tells you Fahrenheit. F inverse plugs in Fahrenheit and tells you the Celsius, okay? So when they say find the value of F inverse of 10, if you made a new F inverse chart, you would just look for the input of 10, and you would get that answer is negative 12 and 2/9. If you didn't make an F inverse chart, if you're understanding inverses well, you would understand that the input of the inverse is the same as the output of the original. So you would have been looking here to find the 10. Notice it is still associated with negative 12 and 2/9. Okay. And then explain what this value means. So F inverse takes Fahrenheit and turns it to Celsius. So we started with a Fahrenheit. So this means 10 degrees Fahrenheit is equivalent to negative 12 and 2/9 degrees Celsius. Okay. And so that's it for inverses. We'll have some homework on this and we'll do a little quizzes for practice in class.